All right, here we are in the third lecture going over the practice final. This is problem number 7, but we've gone through 12 problems already. The first 6 were numbered separately. So went through 6 and then 6, and now we're starting on 7 of the last 18 problems. Number 7 here is sort of an anthology of short problems, most of which just require one formula. So let's go through them. 7a says, find the work to expand 1 mole of an ideal gas from 1 liter to 10 liters at a constant temperature of 500 K. So that's a constant temperature, reversible expansion of an ideal gas. The formula for that, it's just a plug-in problem. The formula for that is minus nRT log V2 over V1. You plug the numbers in. 1 mole, temperature of 500 K, yes. And V2 is 10, V1 is 1, and that gives you minus 9.57 kilojoules. Second problem is also simple. Find the enthalpy change when 10 moles of liquid water are warmed from 300 K to 320 at a constant pressure of 1 atmosphere. The molar heat capacity at constant pressure for liquid water at this pressure is about 75 joules per K per mole. So again, just plug into the formula. Delta H in this case is the same thing as heat, right? Because it's constant pressure. It's the number of moles times the heat capacity at constant pressure times delta T. Delta T is 20, heat capacity 75, 10 moles gives 15 kilojoules for that warming process. Number C says, find the entropy change for the same problem as above. Again, the formula in that case is just the number of moles, the molar heat capacity at constant pressure, log T2 over T1. The temperature changes from 300 to 320, so 320 on top, 300 on the bottom, and that gives 48 joules per K. The last one's just a little bit more difficult. It says find the probability for the highest energy state, P3, of a system that has just 3 quantum states. The energies of the quantum states are 0, kBt, and 2 kBt, so they have equal spacings again. The first gap is 1 kBt, and the second gap is also 1 kBt. The formula we want to use is P equals e to the minus energy, right, which is U3 in this case, over kBt divided by Q. So we need Q. Q is just the sum of these exponentials for all 3 states, and so that's a 1 because it's the energy of the bottom state is 0, so e to the 0 is 1. Then e to the minus 1 because U2 is kBt, right? So it's kBt over kBt, so that's e to the minus 1. U3 is 2 kBt, and so it's e to the minus 2, and that gives 1.503 for Q. Now we just have to plug in to e to the minus U3, that's e to the minus 2 again, same as this guy, and that gives a probability of 0.09 for being in this top state. This is a kind of an illustrative case because notice that the energy gaps in this case are chosen to be equal to kBt, and it's 0.09 because basically because the probability of getting up here is pretty low, and then you're starting from here, so to speak, and the probability is again low to go up to the next level. So, all right, about 10%, a little less than 10%, 9%. Problem number 8 says, find the energy of interaction, capital U, between the 2 molecules below. So notice that this is the one molecule, this is another molecule, this black bar here is a bond, and that means the energy of interaction doesn't include the interaction between the atoms that are inside the molecule already. It's just the energy, it's just the interactions between molecules in different atoms in different atoms. And it's the Leonard-Jones potential. It's van der Waals interaction that we're calculating. For the Leonard-Jones potential is here, right? It's this kind of complicated formula, but it has two parameters. One is the depth of the energy well, the other is the position of the energy well, Rij. Rij is 2 angstroms in this case, and the depth is 5 kilojoules per mole. So we've got to calculate 4 different interactions, 2 of which are the same. This one and this one are the same, and 2 others of which are also the same. So it's just 2 times the interaction at 2 angstroms plus 2 times the interaction at this longer distance. And this distance is 3 angstroms from here to here. And so this longer distance is 2 squared plus 3 squared square root, right? And that turns out to be 3.61 angstroms. So we calculate, first of all, this first term. That's the energy at 2 angstroms. But 2 angstroms, remember, is the minimum depth. That's the position of the minimum, which has a value of minus 5 kilojoules per mole, right? We're at the minimum, so this minimum energy parameter applies. The other one is at a farther distance, so we have to plug into the formula. R is now 3.61. Rij here is 2, and that's 5. And so plugging the numbers in, we get minus 0.285 kilojoules per mole. Notice how much difference a relatively small difference in distance caused, right? These are 2 angstroms. These are 3.6. Okay, that's a fair distance longer, but it's still a pretty short distance, and yet the energy of interaction dropped from 5 to 0.3, more than a factor of 10. That's because the van der Waals interactions are very short ranged. The sort of relevant term is this r to the 6th power here. So yeah, 6th power is going to make for a very short range, sharp and steep kind of interaction. Anyway, now we've got the 2 numbers we need, these 2 guys. Plug them into this up here, and that's 2 times minus 5, 2 times 0.3, minus 10.6 for the overall case. Then it also asks, what's the probability, given that energy, given this energy, what's the probability of finding these 2 molecules close together like this versus being at infinity? So if we take them to infinity, then all the van der Waals interactions are 0, right? So the energy at infinity is 0. So the ratio, this is its relative probability. That means take the ratio here. The ratio of probability close versus probability far is just e to the minus energy close over e to the minus energy far. But the energy far is 0, so this is just a 1 in the denominator. So it's just e to the minus this energy over kBt, and plugging in, that gives 69.3. So just not counting any entropic effects, right? If you just hold these guys steady and move them out to, so they can only move on a line, right? Move them out to 0 and ask what's the probability of finding them far separated versus close together. They're almost 70 times more likely to be together because the sticking is reasonably strong. That's the end of number 8. Number 9 is a little bit more complicated. It's a situation where you've got a protein called A, and it's got a binding site on it, and then you've got a peptide with 4 amino acids. So 1, 2, 3, 4, 1, 2, 3, 4. And 2 of those amino acids can bind to the 2 sites, the 2 amino acid binding sites on A. And when they do, there's an enthalpy of binding, which is 10 kilojoules per mole per amino acid. So that's, of course, so it's minus 10, minus 20 kilojoules per mole of sticking enthalpy when these 2 guys stick, when these 2 guys bind. But at the same time, these 2 residues get locked into place. These 2 residues are fine. The 2 that don't stick don't lose any entropy, but the other 2 get locked into place and they lose some entropy due to internal rotation, like in many other cases. So it says the binding freezes the configurational freedom of the 2 bound amino acids, but leaves the other 2 free to adopt all chain configurations. If each free unbound amino acid can adopt 6 configurations, then what's the standard free energy of binding at 300 K? Well, we know delta H, that's minus 20 kilojoules, 20,000 really. We need delta S though. We don't have that. We have to calculate that from the information we have about the configurations. But delta S is R times log of however many states there are when it's bound versus however many states there are when it's free. Well, only 2 of the amino acids are free when it's bound, so that's 6 times 6, or 6 squared, for the 2 free amino acids. But it's 6 to the 4th when everything is free, when the whole molecule is free. And so this is 1 over 6 squared, which is minus R log 36, right? It's R log 1 over 36, which is minus R log 36. And R log 36 is minus 29.8. So plugging the numbers in, minus 20 minus T is 300 times R delta S gives minus 11.06 kilojoules per mole. And then it asks, so that's the delta G, then it asks what's the KD for binding between P and A. KD is a dissociation constant, of course, so the K is e to the minus delta G of dissociation between the two, but what we calculated above was delta G of binding, which is minus the delta G of dissociation, so it's e to the plus delta G of binding, and that's e to the plus R minus 11.06 over 8.34 times 300, and that gives about 0.0119. So the KD is about 1 over 100. It's 10 to the minus 2, really. So it's 10 millimolar sort of affinity, which isn't very high, of course. You can easily get nanomolar affinity when in some of these binding cases. So it's a very weak binder, which isn't surprising, right, because 2 amino acids is not a very big binding site. All right, that's number 9. Number 10 starts with part A, a very simple problem. Just it asks for the fraction of protein bound to ligand if L is equal to 100 nanomolar and the KD is equal to 30 nanomolar. That just uses our standard formula, F is equal to 1 plus KD over L. Plugging in the formulas, that gives 77% of the protein will have a ligand bound to it, most of it, but not nearly all. Then it says another protein has 2 ligands, L1 and L2. The KD for the first one is 5 micromolar, and the KD for the second one is 1 micromolar. It asks to find the free energy of binding for both ligands binding at the same time. That means there's going to be a delta G for the first one and a delta G for the second one, and we could calculate it that way, right? Delta G for both is just the sum of the delta G's for each one, since they're independent, in fact. There is no cooperativity. And we could say minus R log KD1 plus a minus R log KD2, and that would work. But I did it a different way. Instead, I calculated the overall KD, which is the product of the 2 KDs, right? Because you can think of it as 2 reactions, the binding of ligand 1 and then the binding of ligand 2, and so the product of the 2 KDs is the overall KD. And that's 5 times 10 to the minus 6 for this KD, 5 micromolar, right? So that's why the 10 to the minus 6 is in there. And 1 times 10 to the minus 6 for the other one, which gives 5 times 10 to the minus 12 for the overall KD. And now I use this formula. Delta G of binding is equal to minus the delta G of dissociation, right? If I take the log of KD, I'm calculating a delta G of dissociation. So I put a minus sign in front. And that gives all of that, which is minus about 65 kilojoules per mole. All right, that was number 10. Number 11 is quite a long one. It says, a candidate for a transcriptional regulator R is found to bind to a double-stranded DNA at a specific site A, near a promoter gene, so this is presumably a transcription regulator of some kind. It can also bind to general DNA of any sequence, so it's got weak binding independent of sequence, which means it can bind all over the place. There's lots of sites, lots of weak sites, but only one strong site at A here. But the binding is weaker, as shown in the contributions to delta G below. So all the entries are in kilojoules per mole. So then it gives us a table of the various different kinds of energies that contribute to the binding. For the A site, there's a contribution of minus 10 kilojoules per mole for electrostatics. The DNA gets bent when the protein binds, and that's not as bad for the A site than it is at general. In general, the protein gets bent worse. Presumably the A site already has a bend. DNA can bend on its own depending on the sequence. Certain sequences are already bent, which would make the A site favorable for a protein that wants to bend the DNA. And then there's hydrophobic effect. So the protein presumably has a hydrophobic patch of some kind that gets covered up when it binds. There's hydrogen bonding, which works at the, which does something minus 10 net when you're binding at the A site, but doesn't do anything when you're binding at a generic site. And then there's a whole bunch of other contributions which amount to minus 20 and minus 15. The net result, the total of all those, is minus 55 for binding to the A site and minus 30 for binding anywhere else. Notice that the numbers, the delta G's aren't terribly different, right? There's a zillion A sites, there's a zillion generic sites and only one A site, and yet the delta G for binding to the generic sites is comparable, at least, to the delta G for binding to the A site, and the lesson for that is, as we'll see below, that doesn't matter. You can still saturate the A site. All right, so the next question says, find the KD for binding to both types of sites at 310 K, 37 degrees Celsius, right? Body temperature. So KD for the A site is e to the plus delta G of binding, right? That's what this is, delta G of binding here, over RT, and that gives 5.4 times 10 to the minus 10. So nanomolar affinity, a little better than nanomolar affinity, right? And then in general, for the general site, it's 8.8 times 10 to the minus 6, which is micromolar affinity, actually about 10 micromolar affinity, so much worse. You notice that this relatively small delta G difference has caused a factor of 10 to the 4 difference in more than 10 to the 4, actually, more than 10,000-fold difference in the binding, in the KD of the binding. All right, if the R concentration is about 10 nanomolar, that's our gene here, our regular gene. What fraction of the time would A have an R bound to it? And the answer to that is, I always rederive these formulas just to make, because there's so many different possible fractions of something over something, that I always rederive just to make sure I've got the right thing. So the fraction is the amount of stuff that's bound to A over the total amount of A, whether it's bound or not. And that is equal to 1 over AR plus 1, but we know from the equilibrium constant that A over AR, this much, is equal to KD sub A over R. And so we can plug that in here. Our fraction is 1 over 1 plus KD over R. We know R, we know KD, so it's just a matter of plugging in, and we get 95% saturation at an R concentration of 10 nanomolar. So A is 95% saturated if the concentration is 10 nanomolar, and that leads us to the next question down. If there are 500,000 general sites for each A site, so there's only one A site, let's say, but there's 500,000 of these weak guys, what fraction of R would be bound to them, to the rest of the general sites? This does not have a pat formula. Think about it carefully. So that's a warning. right? That's a warning to say you have to derive the formula in this case. You can't just look on your cheat sheet and take a formula, because that formula isn't on your cheat sheet. We haven't talked about it before. So what is this fraction that we want? We want the fraction of R that's bound to all these weak sites. That means we want the fraction of R's, concentration of R's that are bound to G, that's Rg, divided by the total concentration of all the R's, that's the amount of free R plus the amount that's on G plus the amount that's on A. G is general here, right? And so dividing through by Rg on the top and on the bottom, that's 1 over R over Rg plus Ra over Rg plus 1. So far so good. Now let's use our equilibrium constants. We have the Kd for the general site is R times G over Rg, and therefore R over Rg, which is one of the things we need, is Kd over G. So that much we have. From the other equilibrium, Ra goes to R plus A, the binding to, or really the dissociation from the A site. Same thing, right? R over Ra is equal to Kd over the A site, and so that can go in there. Plugging that, no, sorry, I take that back. That can't go in there, right? That's R over Ra, but we need Ra over Rg. But look, if we multiply this guy by this guy, wait. No. If we divide this guy by this guy, the R's are going to divide out, and we're going to get Ra over Rg, which is what I'm doing here, right? This is Kd over G times A over Kd over KdA. And now that can go in there. This is the quantity or the expression that we need to make a viable calculation. And that gives us a final formula for the fraction, for the thing we want. Fraction of R's bound to the general sites. It's Kdg over G. We know Kdg, we know G. We know Kdg and we know G again. We know A and we know Kda. And you can simplify it a little bit, but you don't really need to at this point. The general concentration is 5 times 10 to the 5th times 1 mole, not nanomolar, right? It says 1 site per cell, effective concentration of 1 nanomolar. And the A itself is just 1 nanomolar. Plugging those numbers in, we get 0.95. So 95% of the R is bound to the general sites, but at the same time, the A site is 95% saturated, which means that this regulator would be doing its job. It would be either blocking or stimulating transcription, depending on what it's supposed to do, even though most of it is bound at general sites. And I think that's a common situation inside all cells. That's why I put this problem in. All right, that was a hard one and a long one. But it's a warning, right? Don't rely entirely on your cheat sheet or on memorized formulas. Be ready to derive a formula, a short one, if you need to, if the problem is asking for something that isn't one of the standard problems. All right, last problem for this session, number 12. It's, again, a little bit of an anthology of different problems, short problems. First one says, using the initial rate data below, here's a table of initial rate data, find the rate law for A plus B goes to C, including the value for the rate constant. So it's a standard problem. You've got 3 values for A and B and velocities for each of those cases. In the first case, A doubles, but B stays the same, and so look what happens when A doubles. Now, there are formulas for this, but I didn't use it in the key here because it turns out that this is such a simple case we don't even need the formulas, because you can look at the data and see what's happening. It's always nice when you can do that, so let's do it that way. Otherwise, there are those standard formulas, and we've done problems like that before, so it's good to look those up because this trick doesn't always work, but when it does work, it's quick. So we double the A concentration. The B concentration hasn't changed. And look what happens. The velocity goes up by a factor of 4. The only way that could happen is if the rate law depends on the square of A, right? V quadruples when A doubles means second order in A. When we look at the next pair down between, when we look at, let's get rid of this junk. When we compare this line, lines 1 and 3, the A concentration stays the same, but the B concentration doubles, and comparing the velocities for lines 1 and 3, it also quadruples, which means that, again, the V quadruples, which means when the B doubles, which means, again, that it's second order in B, and so the rate law has to be of this form. It's fourth order overall, second order in A, second order in B. Last thing we need is the rate constant. We just solve for that. K is equal to V for line 1. Would also work for line 2 or 3 as long as we put in the right concentrations. So for line 1, the velocity is 0.3, and the concentrations of A and B are 0.1 each, and that gives 3,000. Note the units. You can read the units right off of this formula. This guy has, let me erase. This guy has units of molar squared, right? This guy has units of molar squared. This guy has units of molars per second. That's up here. And so doing the algebra on the units gives molars to the minus 3, seconds to the minus 3, and there's your overall answers. All right, that's part A. Part B says an elementary reaction, 2A goes to P, starts with an A concentration of 0.3 at time 0, but after 20 seconds, that's dropped to 0.25. Find the rate constant for this reaction. The fact that it's elementary and that it's 2A goes to P tells you that it's second order. The 2A goes to P must be second order if it's an elementary reaction. So the fact that it's elementary is important to this problem. For a second order reaction, the integrated rate law is 1 over A equals 1 over A0 plus KT. So we solve for K, right? It's asking for the rate constant. We solve for K. K is equal to 1 over T times 1 over A minus 1 over A0. Now we know all these numbers, so we just have to plug in. And we get 0.033 second order rate constant units, molar to the minus 1, seconds to the minus 1. Part C is a standard Arrhenius problem, right? We have a rate constant, 20 seconds to the minus 1 at 300, 40 seconds to the minus 1 at 310. Look also, it obeys the rule of thumb exactly. The rate constant doubled when the temperature went up by 10 degrees. That's the rule of thumb, and we know that when the rule of thumb applies, the barrier height, the energy of activation, is going to be about 50. And so we do the calculation. Here's the standard Arrhenius formula. Plug in the numbers. For 2, right, K2 over K1 is a factor of 2, 40 over 20. And plug in the 310 and the 300, and you get 53.6, close enough to 50. So the rule of thumb already told us. And when you get this answer and you've noticed the rule of thumb, you can be very confident that that's a good answer. Next we solve for A. That's K1 over e to the minus EA over RT1. Notice I'm using the 300 Kelvin case, but we could use the other case, the 310 case, so you should get the same answer. And you get 4.3 times 10 to the 10. And that is it for this session. We'll go on to the next 6